Hello everyone, my name is Aaron Meyer along with my partner Ryan Johnson. This video will detail the work done for our Stormwater Management and Design class. Our work dealt with examining the feasibility of creating a robust monitoring scheme for the stormwater system at the University of Utah. Our goals, project process, and results are summarized in this video as well as in the associated report. Specifically, our aim with this project is to answer the question, what is the predictive accuracy of a model calibrated using the rational method when evaluated against empirical stormwater observations in a complex urban setting? To answer this question, we conduct a case study on the campus of the University of Utah. Previous student work provides a working swim model which was calibrated using the rational method. This swim model will be run using collected storm data to predict runoff and water stage at specific manholes. The bulk of this project is composed of the following: identifying applicable sensor locations, designing and installing a monitoring sensor network, and collecting empirical storm data. The initial scope then proposed calibrating a model using these observations. The results as given by the rational method calibrated model would then be compared with those given by the empirically calibrated model. However, due to a lack of data, as only one very small storm occurred during data collection, the scope was slightly narrowed to eliminate the empirical calibration of the swim model, as a single storm calibration would likely cause skewed results. Therefore, the comparison portion of this project was reduced to comparing the empirical sensor results with the rational method model results to determine the model's accuracy.
We begin by examining our project location and the documents available to aid our research. The image here illustrates the main stormwater trunk lines and manholes at the University of Utah. In order to maximize the drainage area the sensors will be monitoring, we investigated possible sensor locations, starting with the manholes furthest downstream, near 500 South. These investigations involved attempting to remove manhole covers at potential sensor locations. Those removable manholes were examined for sensor installation feasibility. Some, like those seen here, were good candidates due to their relatively simple design: an inlet and outlet pipe with a sump, resulting in a flat water surface. Conversely, some pose challenges to installation and sensor design due to their unique geometry, multiple inflows, or shallow depth below the ground surface.
After investigating approximately 10 potential sensor locations, 3 final installation points were chosen for their ease of install and compatibility with the proposed sensors. The first location lies on the trunk line just north of the Utah Museum of Fine Arts and is seen here. Location 2 is located outside the Thatcher building near the field house, and location 3 is on the sidewalk just east of the university's football stadium.
Once a multitude of possible locations were identified, alternatives for sensor development were evaluated. The 3 design considerations were the following. A capacitance style sensor returns a depth of water contacting the sensor strip. This type requires submersion in the flowing region. Another option was a pressure transducer located at the bottom of the pipe or manhole. The depth of water would then be determined by calculating the force applied to the pressure sensor and correlating to depth. Finally, an ultrasonic distance sensors were considered, which use sonic waves to detect the distance from the nearest object. These would be mounted in the manhole or pipe and provide the distance to the water surface level, allowing for a depth measurement without any submerged parts. In determining the most feasible sensor design, the following design limitations were considered. University facilities instructed us that any sensor must not be intrusive or block flow in any way. The entire unit must be waterproof, including the connection to the data logger. The sensor must have a low risk of being dislodged by high flows. The design should be relatively simple to install and access, and the sensor should be able to reliably sense water depth during turbulent flow conditions. With these restrictions in place, capacitance tape was eliminated as an option due to unreliable readings during turbulent flow and the necessity of having multiple parts and connections submerged. This creates a high risk for dislodging and waterproofing. The same restriction eliminated the pressure transducer option, leaving the unintrusive and unsubmerged ultrasonic sensors as a clear frontrunner.
Further investigation into the functionality of possible ultrasonic sensors was necessary to ensure accurate monitoring. The first type of sensor used is a Maxbotics MB7383. These sensors send sonic waves from the sensor cone and record how long the waves take to return to the cone after bouncing off an object, from which a distance is calculated. However, Due to the wide beam width and the fact that the sensor returns the distance from the first object contacted, incorrect readings would be returned in a configuration like this one, where the sensor beam width would contact the sides of the pipe before the actual water surface. Enter the EchoPod DX10, whose beam width of 5 centimeters made sensing the bottom of a curved pipe like this much more accurate. This sensor, however, requires a mounting point much closer to the pipe, as the range is a mere 1.25 meters. Based on these limitations and advantages, the Maxbotic sensors were implemented in the two wider manholes at locations 1 and 2, and the EchoPod was chosen for location 3. Once the two ultrasonic sensors were decided upon, they were configured for field data collection. We utilized EnviroDIY's Mayfly board as the hardware recording device for sensor output. This configuration consisted of the ultrasonic sensor connected to the Mayfly board, an onboard SD card and battery for time clock synchronization, an external battery for board and sensor power, and a waterproofing design to be discussed later. The Mayfly board is compatible with Arduino-based software, and code was uploaded such that each Mayfly records a timestamp and the ultrasonic sensor's distance measurement to the onboard SD card. These data are recorded at a frequency of 1 data point every 10 seconds. While this short interval is perhaps overkill, the sensors often report spikes producing bad data. This requires many points to be discarded during the data sanitation process.
Once the sensors and data loggers were functioning as expected, the necessary connections were soldered and waterproofed. The mayflies, batteries, and connections were housed in a waterproof Pelican case with cable gland inserts. Finally, the cases were mounted to a PVC pipe for easy install. Sensor installation is configured using a modular PVC chassis design for both the case and sensors. With the help of university facility plumbers, ladder brackets were hammer drilled into the manhole walls, and the PVC chassis was mounted using new rail fittings. Slight modifications were necessary at each site. For example, at the stadium site, the unsupported upper chassis near the case was secured to the wall using foam. Each ultrasonic sensor was installed in the center of the manhole or pipe, with expected distance measurements validated on site. The cases were mounted near the manhole cover such that they could easily be accessed for data gathering, battery swaps, and further modifications. Once the installation was complete, data collection began. During data retrieval, the manhole covers are simply removed and the data from the SD card is downloaded on site. Here, the data is inspected, SD cards replaced, and the battery swapped to begin the next data collection session.
Once the sensors were installed and initialized for continuous data collection, we simply had to wait for rain to test our sensors and hypothesis. And wait we did, until November 20th when a small rainstorm finally hit the Salt Lake region. Open access to weather data is available through the Atmospheric Science Department's MESO West website. Included in the list of stations monitored is one located on the roof of the William Browning building. This gauge allows us to quantify the amount of rain that fell on the university during this time. As seen by the generated graphic, a short period of rain totaling 1/100th of an inch fell on the morning of November 20th, followed by a period of rain in the evening totaling approximately 8/100ths of an inch. Once the storm was over, data was collected from the 3 locations for analysis. Upon collection of the sensor near the Fine Arts building, it was discovered that the sensor was picking up a rung on the ladder within the storm drain instead of the water surface itself. Therefore, this data was completely disregarded due to unreliability. We will focus on the 2 remaining stations, the Stadium and Thatcher stations. To process the data, we begin by loading the raw text files into Python and clipping them to the time period of interest. We then remove bad lines of data due to sensor malfunction, convert the distance measurement value given by the sensors to depth, and resample the 10-second data to 15-minute intervals by average. Here we see the raw data. Clearly, the Maxbotic sensor is throwing a multitude of impossibly high and low values. The EchoPod data looks much less nasty, however, there are still a few outlying spikes. By hard-coding a spike filter between the highest and lowest possible values within each applicable manhole, we are able to successfully eliminate the bad data. And we can clearly see the 2 periods of rain in the morning and evening as shown in the rainfall graph. Next, we used the known zero-depth distance to convert the distance measurement as reported by the ultrasonic sensors to a depth in feet. These values represent how deep the water is flowing through the downstream pipe at each manhole. Finally, we downsample the data to represent an average along 15-minute intervals. This smooths out much of the noise and gives a more reasonable representation of the depths in the pipes. This is the data we will use to compare to our model results. We now turn our attention to the SWIM model. Using MesoWest's data API, the rainfall time series was downloaded for November 20th and averaged to 15-minute intervals. This time series was then associated with the model's rain gauge. The model was run successfully, and the results for the two manholes of interest, J31 as the Thatcher manhole and J18 as the Stadium manhole, were exported to be visualized using Python. The plots generated show the predicted depth as reported by the model in black versus the empirical data collected in orange and blue. As we can see, the results follow the expected trend, however, with some error in both locations. Interesting to note is that in the Thatcher location, the SWIM model underestimates the peak depth by approximately 38%, while at the Stadium location, the model overestimates the peak depth by approximately 37%. Despite these discrepancies, the model does a fairly good job of predicting the timing of the runoff. One note are the non-zero values before and after each period of rainfall in the empirical data. The reasoning for these values is not exactly known, but can likely be attributed to one or a combination of small and variable base flow, inaccuracies in the sensors, inaccuracy in the measurement of the zero depth, or obstructions in the ultrasonics range. We also set out to compare the expected flow values against those produced by SWIM. To do this, we employed Manning's equation seen here. This allows us to calculate the flow in each pipe given the depth recorded, the pipe diameter and roughness, and the slope of the pipe leaving the manhole. The results seen here look awesome for the Stadium station on the right, where the depth of flow in the pipe was directly measured. Recall that there is no sump at this location. While the Thatcher flow has a much higher error. Our inclination is that this error is caused because we are measuring the depth in the manhole and not the pipe directly, potentially missing some head loss. All of this analysis leads us to recall our initial research question. What is the predictive accuracy of a model calibrated using the rational method when evaluated against empirical stormwater observations? Given the results in the previous slides, we find an accuracy for depth of approximately plus or minus 40%. However, this result should be taken with the following caveats. Only one storm's worth of data was collected. Therefore, any outlying errors are amplified due to the inability to average across multiple storms of multiple sizes. The storm that was collected was very small, with less than 1/10 of an inch of rain falling within the day. This means that all measured depths were fairly shallow, and due to the nature of the precision of the sensors, measuring differences of very shallow depths is less accurate than deeper flow depths. Sensors produce fairly noisy data, including some outlier values. More work evaluating the sensitivity of the sensors when sensing turbulent flow and applying more robust signal processing filters would likely reduce the noise and create more accurate results. Finally, there are many potential model inaccuracies. Flow into the trunk line from Fort Douglas is assumed and not modeled, and any new construction that has taken place was not taken into account. The project we have discussed here lays the groundwork for a multitude of potential future projects and studies. This includes collecting more data from a variety of storms for data comparison, using the empirical data to calibrate the SWIM model and comparing its performance, developing an above-ground station at the manholes with a solar panel and connected Wi-Fi data transfer such that frequent field visits become unnecessary, configuring automatic data uploads to EnviroDIY's Monitor My Watershed program to provide data for others and compare with similar projects, deploy more sensors in critical locations, and add more modular sensors such as water quality or flow to the existing design. This project has laid a good foundation and proven the feasibility of the idea. Future work can build on this foundation and create an even more meaningful dataset for analysis. We'd like to specifically thank those who were instrumental in the success of this project, especially Dave Erickson, whose knowledge in the field of water sensing proved invaluable, Facilities Engineer Stephanie Brown for coordinating the sensor install, Alicia Urbaniak and Logan Lawson, the facilities plumbers who assisted with install and data collection, Emerson Andrews and Michael Brem for their assistance in helping us secure a SCIF grant for funding the project, Dr. Carlos Arosa for letting us use his lab, sensors, and equipment, and Danny Zebelian for her work on the SWIM model. Feel free to contact us with any questions you may have about this project, and thanks for listening.